This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about the problem solving on simple stresses and strains. So we are discussing about the solid mechanics and material subject. So in this subject already we have studied various stresses and strains and the relations between the simple stresses and strains. Now in this session we will see how to solve the problems on simple stresses and strains. Already previous session we have discussed some problem models. So now in this session we will see some more problems. So first of all, you should know the course outcome. The student should be able to explain the concepts of stress strain and then material constitutional relationship, strain energy induced in the linear, elastic, and homogeneous and isotropic materials subjected to forces. So whenever the material is subjected to some load, there will be a deformation and some strain energy also induced inside the material. So these concepts, after completion of this module topic, the student should be able to explain all these concepts of stress strain, material constitutional relationships, and strain energy induced in the linear or elastic, homogeneous, and isotope materials. So the problem solving on simple stresses and strains, the introduction is first recall the stresses and strains. So when an external force acts on a body, the body tends to undergo some deformation. So due to cohesion between the molecules, the body resists deformation. So this resistance by which material of the body opposes the deformation is known as strength of material. So whenever the external forces acts on a body, the body tends to some deformation. So why? Because due to the cohesion between the molecules, the disturbance will be happened inside the material. So the body resists the deformation. This resistance by which material of the body opposes the deformation. So that is called as strength of material. So now, but behind this elastic stage, the resistance offered by the material is less than the applied load. So in such case, the deformation continues until failure takes place. So already you know the stress strain relationship. So according to Hooke's law, the stress is directly proportional to strain. So in this, you can write the stress is equal to E into epsilon in terms of Young's modulus. So you can write the E is equal to sigma by epsilon Young's modulus. The stress is directly proportional to strain up to elastic limit. So you know stress strain relationship. The stress strain relationship, the stress strain diagram, you can observe up to elastic limit there is no deformation. So it means the stress, how much stress increase, the stress increases, simultaneously the strain also will increase. So like that up to elastic limit. So behind this limit, some deformation will be occurred. So lower yield point and upper yield point. After this, it reaches the ultimate stress. So that is final, the maximum stress. Beyond this ultimate stress, the component will fail, takes place. So within the elastic state, the resisting force equals to applied load. So the resisting force for unit area is called stress or intensity of the intensity of stress. So, but behind this elastic state, the offered by the material is less than the applied load. So, in such case, the deformation continues until failure takes place. So, within the elastic state, the resisting force equals to applied load. So here, the resisting force per unit area is called the stress or unit of stress. So already we have discussed. So now we will see one problem on this stress and strain. So already we have completed 3 problems in the previous session. So in this, some more problems we will see, and then so the problem number 4. See, in this problem, the given the variable cross section. In previous sessions already we have discussed about whenever the uniform bar subjected to some load, how to calculate the stress and strain and the elongation and elastic Young's modulus we have seen. So in this, an axial flow of 35,000 newtons is acting on bar consisting of 3 lengths as shown in figure. Here 3 lengths given. So the axial pull of 35,000 newtons. So acting on a bar consisting of 3 lengths, so Young's modulus is 2.1 into 10 to the power of 5 Newton per mm square. So in this, determine stresses in each section and the total extension of the bar. The stresses in each section and then total extension of the bar. So each and every section first you need to calculate the stress. And what is the total extension of the bar due to this 35,000 Newton? So how to solve this problem we will discuss here. So the given data, the section 1, the diameter is 2 centimeter. The section 2, the diameter is 3 centimeter. And section 3, 5 centimeter. So the length of the section 1 is 20 centimeter. The second one is 25 and 22. So these are the information given. Now according to the given information, need to solve the problem. First of all, given data. So the given data is load is 35,000 Newton and E 2.1 into 10 to the power of 5 Newton per mm square. And stresses in each section. So given so first you take in section 1. Take section 1. So that section 1 load is 35,000 newtons. Tensile load. So what is the diameter? So the diameter is 2 centimeter. So 2 centimeter convert into mm. So that is 20 mm. So the length of the section is L is 20 centimeter. So 20 centimeter convert into mm. So 200 mm. So how do we calculate the stress? Already we have seen in a previous session. Stress is equal to load per area. So in section 1, stress is equal to load per area 1. So how do you calculate the area? So area 1 is 5 by 4 into d1 square. So here substitute 5 by 4 into what is the diameter? D1 is 2 centimeters convert into mm, so 20 centimeter, 20 mm square. So 2400 square, so 400 here, 100 pi Newton per mm square. This is the stress induced in section 1. In section 2, area calculate and again calculate stress. So now we will see the area already calculated. This area substitute in this stress equation. So the load is equal to 35,000 divided by the area is 105. So already we have calculated. So calculate, you will get Newton, here 100 pi mm square, the area units. So here Newton per mm square will get the sigma 1 value. Similarly, at section 2, at section 2, section 2. So what are the dimensions in section 2? Section 2 3 centimeter dia and 25. 3 centimeter dia and the length is 25. So same load. The load is 35,000. So now here also calculate the stress. Sigma 2 is equal to load upon area 2. So here area, how do you calculate area? 5 by 4 into d2 square. So here area 5 by 4 into diameter is 3 centimeter converted to mm, 30 mm. So 30 whole square. So we'll get area and then substitute in this, the second stress we'll get. Similarly, at section 3, so what are the dimensions? Section 3, 5 centimeter and 22. 5 centimeter and 22. The length is 22. So here calculate area 3, sigma 3. So the diameter is 50. So we will get stresses. What are the stress induced at section 3? Now, so according to the given problem, stresses in each section already completed. Now, I have to calculate the total extension of the bar. So what is the extension of the total extension of the bar due to this load? So already I have calculated section 3, section 1 at section 2 stresses. Now write down the stresses here, whatever you calculated, and then we will go to second part. Calculated values. Write down calculated values sigma 1 and sigma 2 and sigma 3 in Newton per mm square, in Newton per mm square, in Newton per mm square. So here P by A1, P by A2 and P by A3. The second part is elongation of the bar due to this load. So how do we calculate the elongation? So you know the stress is directly proportional to strain, and then the stress is equal to E into sigma. Already I told you in the first slide. E is equal to sigma by epsilon, strain. The stress upon strain. Now, the stress calculated and strain is delta L by L. Strain is equal to delta L by L, change in length by original length. The stress is equal to load upon area. Now, substitute this strain and stress values in this equation. E is equal to stress is equal to P by A upon delta L by L. So now you can write this equation. E is equal to PL by A into delta L. So E into A into delta L is equal to PL. So delta L is equal to PL by AE. So this is the change in length is equal to PL by AE. So now what about, so you need to calculate the change in length in first section, delta L1. So that is P L1 by A1 E. The E is constant. Next delta L2, P L2 by A2 E. Delta L3, P L3 by A3. So now here PL by AE and then PL1 by A1E and delta 2 is PL2 by A2E and delta L3 is PL3 by A3E. So these are the elongation due to the load in first section, section 2 and section 3. So what he has asked, the total elongation of the bar due to this load. So now the total elongation is delta L1 plus delta L2 plus delta L3. So now you can write delta L1 PL1 by A1E plus PL2 by A2E plus PL3 by A3E. So now, rather than this equation, take common, load is common and E also common. So now L1 by A1 plus L2 by A2 plus L3 by A3. So now you can substitute given values 35,000 Newton E into 2 into 24 5 by what is the L1? In first section, the L1 is 20, L2 is 25 and 22. 20, 25 and 22. 20 A1 5/4 into D1 square plus L2 25 by 5/4 into D2 square plus 22 by 5/4 into D3 square. So here the length is in cm, convert into mm, 200, 250 and 220. So now already you know the area calculated in the first slide, first problem. 5/4 D1 square and 5/4 into D2 square. So those values here substitute, you will get total elongation of the bar. So this is the total elongation of the bar delta L. So like this, need to calculate this type of the problems. So whenever the bar is not in uniform, so that is it means the variable section. So separately need to calculate and finally add all these elongation, you will get total elongation. The next model, so the relationship between the elastic constants. In an experiment, the bar of 30 mm diameter is subjected to a pull of 60 kilonewtons. So the measured extension on gauge length of 200 mm is 0.09 mm and the change in diameter is 0.0039 mm. So calculate the Poisson ratio and then the values of the E, C and K. So here solution given, so I will explain clearly here. So first of all, given data, thirty mm diameter given D and a full of 60 kilonewtons. The measured extent, take one empty slide, I will explain here. So already here mentioned. So the given data diameter is 30. So 30 mm or mm. So and then 60 kilonewtons. So in this given data, diameter is 30. Mm and load is 60 kilonewtons and the measured extension of gauge length is 200 mm is 0.09 mm and change in diameter is 0.0039 mm. So the gauge length is The gauge length is 200 mm. Gauge length 200 mm, and the change in length is 0.09, and change in diameter is 0.0039, and then the Poisson ratio need to calculate, and then E, C and K, the values need to calculate. So now in this case you can calculate area 5/4 into D square. So already you know the D 5/4 into 30 square. So calculate, you will get area in mm square. And then need to calculate the Poisson's ratio. So that is 1 by m or mu. According to the Poisson's ratio definition, it is a ratio of lateral strain by linear strain. So here delta D by D is the lateral and delta L by L is the linear strain. So calculate delta L by L, and delta L 0.09 by L 200. So we will get lateral linear strain, and the diameter delta D 0.0039 divided by diameter 30. So you will get, and then find out the Poisson's ratio. And then, so what are the E and C and K values? So here E is equal to sigma by stress by strain, or load per area by delta L by L. So PL by A into delta L. P given, you know, and L also, you know, and delta L and area. So you can calculate the C value. And C and K. So what is the relation between these two? And C and K, you can recall, already we have derived in first session. So ME by 2 into M minus 1, and K is equal to ME into 3 into M minus 2. So what is here M? M is the Poisson's ratio. So already we have calculated the Poisson ratio. Those Poisson ratio substitute in this values, you will get EC. So like this, you need to calculate the elastic constants. So whenever the component material is subjected to various loads. So these are the references I have taken. Ramamurtham, Strength of Materials, title of the book, and Dhanapati Rai Publishing Company, and R.K. Bansal is the textbook of Strength of Material, and R.S. Kurmi and Gupta, Strength of Material title, and then Chand and Co. publishers. So take one reference for more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.